In this video, we're going to go over the basics of prime numbers. Of course, the definition of a prime number is a number whose only factors are 1 and itself. On the screen you can see all the prime numbers up to 1,000. 2 is the first prime number. That's the only even prime number because any even number after that would have a factor of 2. So after that, they're all odd numbers. 2, 3, 5, 7, 11, and most of us know those primes, and it goes up from there, and all the way up to 997 is the last prime that is less than 1,000. The reason prime numbers are so important is because of the fundamental theorem of arithmetic, which says that every number can be written as a product of primes, and in fact can be written as a product of primes in only one way. So, put another way, the prime numbers are the basic elemental numbers. They are the basic ingredients of all numbers, at least from a multiplicative standpoint. So, for example, if we take a number such as 168, that is not a prime number. It's even, for example. But we can try to think of the factors of 168. For example, we can break it down into 8 times 21. Now 8 can be broken down further into 2 times 4. Now 2 is a prime. It can't go any further. 4 can be broken down into 2 times 2 primes. Meanwhile, 27 can be broken down into 3 times 7, and they are both primes. So we can't go any further breaking down these bottom numbers into primes, so we're done. And they are all primes already. So 168 is 2 times 2 times 2 times 3 times 7. So that is 168's prime factorization. And again, this is the only collection of primes that will multiply up to 168. That's not immediately obvious, but it turns out to be true. Just a couple words about the distribution of prime numbers. The primes become more and more sparse the higher you go. So you can just start to see it in our list of numbers, prime numbers up to 1,000. In the beginning here, you see, a lot of numbers are prime, almost every other one in the beginning. But as we go, they get a little bit more sparse. If we're down on this bottom line, we can, there's a gap of 8 from here to here. There's a gap of 10 from here to here. Here's a gap of 14, 953 to 967, no primes in there. That does not happen back here in the earlier numbers. There are, gaps of 2 or 4 or 6 or something like that. So you can already start to see that the primes are getting a little more spaced out. And that stands to reason because it gets harder to be a prime number if you get bigger and bigger, because there are so many numbers before you that could be a factor. There's more chances to have factors if you're a larger number. So the prime numbers do get rarer as you go up. However, it does turn out, you might, the question would come up, well, maybe there's a last prime. Maybe eventually you get to a point where there can't be any more primes. But that is not true. There are infinitely many primes, and that has been known since ancient Greek times. Euclid supplies us with a proof that I won't go over here, but it's not too hard to see that there's always more primes. There's no biggest prime. You can always find another prime beyond whatever prime you're at. But knowing that there are infinitely many primes is great, but what is the distribution? How dense are they in the numbers? And so now we come to a very famous fact, much more recent than ancient Greek times, which is called the prime number theorem. And it says that the percentage of numbers less than x that are prime is approximately 1 over the natural log of x. So if you look at all the numbers up to x and you ask, okay, what percentage of them are going to be prime? This formula will be a pretty good approximation. And when I say pretty good, when I say approximately, I mean that the bigger x is, the closer this will be to the true number. So let me show you that in detail. So we had looked at the primes up to 1,000, but if I just back up, if you look at all the primes up to 100, it turns out that 25% of them are prime. That's easy to just check by brute force with a computer. For 1,000, it's 16.8%. so it has a decimal point 168. Up to a million, it's between 7 and 8%, and so on. You see I'm going up to a billion, to a trillion, and the fraction that are prime up to that point is getting smaller. So that goes along with the point we made earlier that the primes get rarer and rarer. Now, in the meantime, if you calculate 1 over natural log of x, if you just plug in the x into this formula, here's what you get. So for 100, you get 0.2171. That's pretty close. That's in the ballpark of 0.2500. For 1,000, 0.1448. That's getting closer to the true number, 0.1680. For a million, you see we're very close. For a billion, and then for a trillion. And if we kept going, you would see these two numbers matching better and better. And so 1 over natural log of x, a very simple formula, turns out to be a pretty good approximation, especially if you're talking about large numbers, for how many of them are prime, or the percentage that are prime. So if we jump all the way to 1,000-digit numbers, numbers that have 1,000 digits in them, so in other words, numbers that are on the scale of 10 to the 1,000 power. So that's an enormous, enormous number. When you're talking about numbers that big, how are the primes distributed? How dense are they? How many of those numbers are prime, roughly? So it would be really hard to actually figure out that number exactly, but with the prime number theorem, we can get a really good approximation. So we can just look at 1 over the natural log of 10 to the 1,000. And it turns out that that equals 0.000434294, and on it goes. So less than 4/100ths of 1%, or excuse me, not less than, but about 4/100ths of 1%. Put another way, that's about 1 over 2,303. So when you're talking about 1,000-digit numbers, the primes are few and far between, and you get one prime about once every 2,300 numbers. Okay, so they're really rare up at that height, at that size of number, but they're still out there, and yeah, about 1 in every 2,300 numbers is prime at that point.